Is it possible to imagine the fourth dimension? I believe that this model proves that making a visual representation of the fourth dimension is so simple and easy to produce that you have probably seen one before without knowing what it could do. The key fundamental is taking two separate images of the same three-dimensional shape from two angles, mirroring the object between shots, and then overlapping those images using a basic method of image manipulation, opacity. This achieves transparency, allowing us to see both images at once. The overlapping cubes you see are in the same exact 3D location, but don't share the same rotation, meaning they don't intersect in 4D space because they do not share the same rotation. The dark zone in the center is the four-dimensional geometry, taking up four-dimensional space from our point of view as it points along the W axis, and every other lighter zone of the image is three-dimensional area. By rotating the original cube or the cameras around the cube, videographing it from the same two angles, we can see that rotation does not change the organization of the dark and light zones. This representation method can be done with any three-dimensional shape, as doing this will achieve the same organization. The reason we don't make the cube see-through is because it is not realistic. Even a transparent cube made of glass is not directly see-through. We can only see the light reflected from the object behind that passes through. For this guide, we'll be using the cube as it is simpler. One cube is the mirror image of the other, meaning we can take one cube, rotate it until we get its mirror image. This means we can do the same kind of rotation with a chiral shape and get its mirror image by rotating it through a fourth higher dimension. As we do the rotation, the shape appears to deform as if it scales instead of rotating. But if you look at how a tesseract shadow rotates, it deforms in 3D but does not in 4D, even though it may seem to. So by this fact, we can know that the seemingly deforming shape is not actually deforming at all. We positioned the cameras diagonally from top to bottom so we could get as much surface area as possible into center frame. Now if you take a look at this cube, you can imagine that the back can be the front. In 3D, only one answer is correct. But in the fourth dimension, there is no rule regarding which of the two options is correct. They are both right. What's fascinating is that on the two cubes model, we can think of the dark zone as a four-dimensional shape. That allows us to correctly say that the back vertex of this four-dimensional space is actually the front and back. We can see the front and back at the same time, meaning we can see through a three-dimensional shape even if it is not transparent. However, there is a problem. To understand it, we'll map out the geometry of the dark 4D zone. To do this, we'll need to introduce two new kinds of geometry. A cube must have at least 8 vertices, so we'll assume that amount because no amount of subdivisions will alter the cube's shape. We'll use black lines for edges and green dots for vertices. The faces are already shaded, so we won't color them. Now there are some conjunctions along the edges that travel from 3D to 4D. At those conjunctions, we'll use the first of the two new kinds of vertex, the phantom vertex. We'll mark them in red. Its name phantom means it does not actually exist in 3D, since we assumed there are no vertices along edges of the cube. But for the logic of the fourth dimension up until this point to continue to make sense, every conjunction on the boundary edge, along an edge, separating 3D and 4D must have a vertex, one that cannot exist yet does. There are also conjunctions along an edge that meets with another edge. There must be vertices at those places too, so we'll introduce the ghost vertex. They're marked in white. The difference between ghost and phantom vertices is that ghost vertices are involved in self-intersection, while phantom vertices are at the boundary between dimensions. You can argue that ghost vertices are irrelevant because they can also be put on self-intersections in 3D that have space between them and therefore should not exist. But since back and forth are both correct in 4D, ghost vertices are relevant because they connect the simultaneous realities of front and back. You can think about each ghost vertex as the central pivot points between each back and forth reality. As the rotation of the original cube in its mirror happens, some vertices merge but don't disappear. We'll mark them like so. Others seem to vanish as they exit the dark zone and reappear as the original cube in its mirror finishes its rotation. In fact, at every point in time, there are vanished vertices. The question is, what happens to the vanishing vertices? We will go over 3 solution ideas. Number 1. Do the vertices simply pop in and out of existence? The simple answer to that is probably no, as it is oversimplified and would destroy geometry, because even in both the 3rd and 4th dimensions, vertices must exist and connect to edges for edges to exist, and edges must be connected to faces for faces to exist. Number 2. So what if the vertices vanish because the dark zone was never 4-dimensional? Now this model does not show us all of the 4th dimension at once, but it can help us understand how we can approach imagining it. When a vertex that makes a 3D shape is over the dark zone, it is on top of an infinite stack of vertices that make the 4D shape. When the vertex travels back into 3D, the infinite stack still exists, and it is still at the top of that pile. We just cannot see the stack from our point of view, so it makes 3D geometry according to our point of view. If we were positioned more towards the side of the vertex so that it would appear in the dark zone again, the stack would reappear. The idea that a 4D object is an infinite stack of 3D objects is supported well in this way. That means the W-axis adapts to whatever view you have, so as to point in the same direction. And number 3, the much more likely solution is that those vertices travel into the invisible part of the 4th dimension. Disappearing in and out of the 4th dimension may seem to mean that all along the dark zone in the center was not actually 4-dimensional. That is not true. The model did successfully identify and explain the logic of 4D by connecting multiple analogies at once, but couldn't show us all of it at every moment in the rotation. So how do we see the invisible 4th dimension? One idea is moving each camera closer to each other so as to enter the dark zone and see what is inside. Another idea is taking 2 separate shots of the dark zone itself, just like we did with the original cube, and then doing the opacity trick on those images. If that works, could we then take 2 shots of the dark zone and do the opacity trick on those images, and so on over and over again to find the 5th dimension, 6th dimension, 7th, 8th, 9th, and so on? And finally, what if you see the W-axis from 2 points of view at the same time? But those ideas are questions for the advanced guide. Take care, keep thinking, and farewell.